right, so thank you very much, Francesco. Thank you everybody for joining this webinar. So I'm going to give you a perspective of some recent work that we have done, myself, the PhD student working with me and other collaborators that I will mention during the talk on the optical properties of molecular switches such as azobenzenes and their crystal counterpart, which means that once they have been attached into some other materials. So our interest is we're interested in materials for carbon capture separations and for gas applications in general. So today, as you know, there is an very active research in developing new materials that can be effect efficiently absorbing and separating CO2 from other gases, like the conventional chemical absorption method, monoethanolamine, which is the only method that for now is being implemented in large scale. Physical absorbance, some mixed membrane composite matrices, ionic liquids, and solid adsorbents. And among these last family of materials, I'm particularly interested in meta-organic frameworks that are three-dimensional materials that are being discovered for the first time in the late 1990s by Omariagi and co-workers. So these materials are 3D networks where there are molecular ionic centers that are connected together by organic molecules. And here we've shown just four examples of different topologies. So they are very interesting because for gas separation because of their porosity, but also because we can have a large tunability of the physicochemical properties by changing the components. So to me, it's very interesting to show that the first MOF was synthesized with permanent porosity in the early 1990s. And today, there are more than 77,000 structures published in the chemical structure database. So let me show very briefly, this is probably the most technical slide on the carbon capture concept, but it's, I think, useful to understand what we do. So usually to establish whether a material is interesting for carbon capture, we look at the adsorption isotope, which measure the amount of molecule absorbed as a function of pressure. So imagine that we are absorbing at low temperature, and this is our adsorption isotope. So the idea is, of course, that you want to have this curve the highest possible, so that you absorb it a lot. And then you induce a temperature swing, so you heat your material, and this is the adsorption isotherm at higher temperature. So the difference between the adsorption at low temperature and the absorption at high temperature is called the working capacity, and it gives how much gas you can effectively capture at each cycle. So of course, what you want is that the working capacity is very large. The problem is that when the working capacity is large, in order to have a large decrease in binding, you need to have a very large parasitic energy associated, which is the energy required to desorb and pressurize a kilogram of CO2. So now there have been some work in the community trying to develop materials that are smart in desorbing gas. So one idea is, can we have a very large working capacity, but without having to induce a huge change in temperature? So with an associated low parasitic energy. So can we use light? In fact, light is cheap, and can we achieve such good performance? Well, the proof of concept was performed in the early 2020 and 12, where molecular photoswitches were used, such as azobenzenes. So photoswitches are molecules that respond to light and they isomerize. So imagine that you can go from, so in this case, you can go from trans to cis upon UV and visible light radiation, and you can go back to trans either with temperature, because trans is the stable form, or by radiating it with a different wavelength. So the authors demonstrated, in fact, that you can functionalize one of the most well-known MOFs, MOF5, with azobenzene, and that upon irradiating it with UV light, and using the photoisomerization from trans to cis, you can drop this absorption of CO2 enormously. So I haven't put this part of our study here, but we showed, in fact, that this huge drop in absorption is due to the fact that when we are in situ, we are blocking the absorbing side of CO2. And another thing that we found is that the larger the number of molecules that you are isomerize from cis to trans, the higher is your drop. So, it is essential now to understand, sorry to go back, how we can increase the photoconversion efficiency, the number of molecules that photoisomerize from trans to cis. So this is given by the composition of at the photostationary state of trans and cis. So this composition depends on the absorbance and on the quantum yield of isomerization. So because the quantum yield of isomerization, which is the probability upon excitation of the given wavelength to isomerize, because this is very similar in the different cases, what changes dramatically is the absorbance. So usually people notice that the efficient photoconversion, you excite in the part of the spectrum where cis, for example, absorb the most, in order to induce photoisomerization to trans, and vice versa. In the UV part of the spectrum, you have a large band of pi star part of trans, and upon excitation, you can have a large fraction of cis. So this means that in order to predict which is the material or design a material that gives the largest change in gas uptake upon light radiation, we need to have a very precise prediction of the optical absorption spectrum. So we work with the many-mode distribution theory. So I won't go much into the detail because I think that in this community it's rather standard. So we start from a constant, from the mean field theory, in order to get, for example, in this case, constant eigenvalues and eigenfunctions. And then we use the green function formalism. We start from the one particle time order green function here in energy representation that fulfills the diazomerism, where the G0 is the green function for the independent particle phase with the associated Hamiltonian H0. And this is the eigenvalue problem, the quasi-particle problem equation, where epsilon and psi n are the quasi-particle energies and wave function that correspond to ionization potential and affinity, so electron removal and addition energies. And the self-energy here is the local energy dependent term that contains the many-body interaction correlation. So within the heading sets of equation, which is a closed set of equation, we work within the GW approximation, which is the lowest term in the expression of the self-energy in terms of W, which is the screen Coulomb potential. And practically we work in a perturbative way, which means that we keep our constant wave function frozen, and we perturbatively correct the constant eigenvalues with the expectation value of the self-energy computed using the constant wave function. We work, so all the data that I'm going to show are eigenvalue self-consistent values of GW, which means that we iterate several times the correction until we are within 0.1 in the energy. And then starting from the Dyson equation that connects the interaction, no interaction to particle correlation function, we write the Bethe-Salpeter equation, which is written here in the eigenvalue problem that recalls the Bethe-Salpeter equation in PDF3, so where omega is the excitation energy and X and Y are excitation, the excitation component on the excitonic wave function, which is written so in terms of electron hole pair using again the constant orbital. So okay. Coming to the results, so the first thing that we did was to compute the optical absorption spectrum of azobenzenes. So we computed this using global hybrid functional by changing the amount of exact exchange from 0 to 27%. So the first thing that we noticed is that there is a huge dependence on the first excitation, the n pi star excitation, while the pi pascal excitation is rather constant. And then this dependence occurs despite the fact that the VGW gap is rather constant throughout tuning of the starting point energy. So so we came with the problem, since we want to be precise in the description of the energy, which starting point function to choose. So we worked with the ionization potential theorem. So we posed that our HOMO equals the ionization potential, which we don't necessarily know, but we do know the GW eigenvalues, which are for us the best approximation to the ionization potential. And by doing so, we impose an exact condition of the density. We impose that our constant density actually decays exponentially the same way as the exact n-electron system. So what we do is that we tune the amount of exact exchange until our DFT HOMO equals to GW eigenvalue. So it's a little bit the similar situation to the optimally tuned range separated hybrids that you probably know. So the difference is that while in that case, it is usually used in order to align the eigenvalues so that we can have good excitation energy within TD-DFT, while in this case, since we know that our eigenvalues are rather constant and well described with GW, what we are interested in the conditions of the wave function of the density. And by doing so, if you look at the table, we see that we can get very good values for all the excitation of transient fits. Of course, with respect to temperature, to experiments and also to coupled clusters. So if I zoom out a little bit in the calculations, we see we perform more of this. And we see that, in fact, this is our value, the alpha G, so tuning of alpha is even closer than, much closer than the PD, for example, that gives it more excitation energy also in PDH, and MO6 is rather good, on the other hand. So now we wanted to validate a little bit more this approach, because most of the values of these experimental values of these excitation energies are found in solution. We adopted an embedding scheme that was developed by our collaborators, Gabriel and co-workers, in which we have a slow, our environment is described both in the DFT, using the polarizable continuum model, for example, where you have both the ionic and electronic contribution to the electron constant. And then we only use the electronic one which accounts for the faster electronic contribution in the GW and BSE. So this is done by calculating the reaction field matrix, which is the reaction of the solvent. It describes if Q is the region in the QM part and N is the MM part region. So the reaction field is computing as a response in point in the QM region due to the presence of the environment NN here. And the response function is computed using the microelectrostatic model in the MESTER code, where the system is described as a system of polarizable points, where the polarizability is given by the Clausius-Mozottin equation starting from the refractive index or from the electric constant, which is the ingredient that we use. So as expected, the fundamental gap of azobenzenes decreases due to the screening of the charged excitation from the IP and the EA. And how about the optical gap? Sorry, I wanted to do an animation, but please look at the beginning just from the top figure here. So you can see that, so the black one is the experiment. So the first calculation that we did is the green one, which is the BSE calculation, where we do this tuning in gas phase. Then we apply embedding, both at the ground state, as explained before, and in the GW, and we see that this excitation moves at higher energy. So if the screening were just due to the GW, we would expect, of course, a decrease in the excitation energy, but we go the other way around, because we have both screening in the GW part in the GST. And then what we did is that we rescaled again our amount of exact exchange in presence of bending. So this is the gas phase part, and then both the BSE and GW change, and so we have a new value of alpha, which is lower alpha E. And when we do this BSE calculation with the starting point of this given by alpha E, we have a very good match of the n pi star produced while the pi is rather constant, as I said at the beginning. The similar behavior was found for the phosphofluorinated azobenzene molecule. So then we computed this optical excitation energy for the S1 for a series of 10 azobenzene derivatives, and this is the result. So the best performance is the PBH alpha E, and you see here that in fact PBE 0 as amount of exact exchange is too small, and these excitation energies are lower than the reference. Alpha G as amount of exact exchange probably is too large, and so you have excitations that are higher, and the best agreement is found with alpha E, as you can see also from this statistical analysis here. So the next part of our work was trying to use this in order to answer the following question. Okay, we want to study MOFs, not molecules. So how do the excitation in the MOFs compare with the molecules? So can we use fragments in order to study these systems, because it will be much easier, just to see, for example, which is the best functionalizing molecule that we want to use, and extend these considerations to the MOFs. So first thing is to look at the density of states, starting from azobenzene, then the ligand, and then different fragments. Sorry, I forgot to mention. So these are the fragments that we use. We have the full periodic MOF, the ligand, which is the smallest fragment that you can think of, P, Q, and R. And you see that, in fact, throughout this this series of models, you have this pi, n, and pi star. These are shown here for the case of azobenzene. So here we have a breaking of symmetry, of course, when you insert your azobenzene into the MOF, because with two phenylene, they're not equivalent anymore. And this is nicely reproduced from the ligand to the full periodic MOF. So when you go to the BSE spectrum, so this is the BSE spectrum of the azobenzene. You have n pi star excitation and very broad and continuous band here. And here what I'm plotting is the electron hole density. So in the case of the full MOF, the excitations, the spectrum is different indeed. We have these states, these excitations that are not present in the ligand because the pi 2 star are not present in this case. So this is breaking of symmetry. And we also see that, the S1 is rather intense. And that, okay, so at low energy, more or less, we have a fair description. But as we go from after the S4 here, the description is kind of fades away. So here I'm going to go into more details of these calculations. Okay, so here now I'm showing the comparison of transient systems, because you remember that we are interested in the selective absorption of one over the other. So what we're interested in is that the energy is correct, but also that the oscillator strength is right. So we see that as we improve the description of the model, the excitation blue shift, and that so all these results here are obtained with PBE, just for the comparison, for an easy comparison. Now, what is interesting is this very intense band, the full MOF that's not present in the molecule, in azobenzene, in the ligand, and that comes from the wave function, because the same trend is found when using independent particle absorption spectra. And then here we use this orbital-tuning, in which the amount of exact exchange is 40%. So we have this linked shift in the energy. So now we can provide the spectral region that have the best in order to excite and have a large conversion efficiency. So here what we find is that so the molecular description is more or less accurate. So here, of course, you have a different amount of reduction change, but is more or less accurate in order to give the qualitative picture, but in order to be computed, you need the full MOF. So now the question is, what happens to the MOF without the azobenzene functionalities? So this MOF, is called MOF 5, and is one of the first MOF synthesized, and is the most studied MOF in literature. And so what it is curious is that although the fact that it's very much studied, there is still a controversy on this issue. In fact, some experiments have found that this material is a semiconductor and that has catalytic properties like zinc and zinc oxide. And sometimes been claimed, in fact, that this is one case in which we have a very good band gap because the optical gap is very similar to the BSE gap. It's very strange function because BSE is not the optical gap. In fact, it's not even the fundamental gap. And one recent study showed that there is a huge similarity in the luminescence of MOF and the ligand that composes it. So I think it's rather kind of difficult to understand the situation because, well, if it's catalytic, you assume that the states that are exposed are the zinc states and not the ligand one. So we wanted to settle this case, and we computed the GW and the BSE to find the optical gap and the fundamental gap. So if we look at the left part first, so this is the density of states. So the BSE, in fact, as I showed before, is reduced with PDE 3.6. With the GAU PD, we found that GAU PD is PDE with the Gaussian attenuation for the Hachikoff exchange. And we see that we have an increase of the gap, and the huge increase, in fact, when we go to GW side to GAU PD. And the fundamental gap is indeed 8 EV. So when you go to the BSE, you find that the optical gap is rather small, in fact. The exciton is composed, is very localized and composed from the S1, we can see here, it's composed by C1, D1, and D2 and C3 excitation. So all these frontier states. And the S2, which is the pink excitation, mainly from C1, from V2 to C1. So the optical gap now is significantly reduced, which reflects a strongly bound exciton. And once we compute the ligand, we see, in fact, in agreement with the experiments that I showed before, that the optical absorption spectrum is very similar to one of the MOFs because the excitation is really localized on the ligand. And it's a very similar situation compared, for example, to benzene, in which we have a fundamental gap of 10 EV and an optical gap of, say, 4.8. Again, this is a slide with more details of the calculation. So it is interesting to see that, in fact, we have computed both the ligand and the MOF. So the ligand, despite the fact that you have different values of the gap depending on the starting point functional, the EV-GW gap is fairly constant. The effect of the embedding is rather significant, it's around 1.4 EV. The optical gap is significantly reduced, and the effect of the environment is more in this case as expected for mutual excitations. So regarding the MOF, now we compare again the periodic MOF, with PD and GAU PD, with two fragments, fragment A and fragment B. So to me, it's interesting to see that, well, that in this case, the MOF, the effect of the embedding is smaller here on the GW gap, and that the optical gap, in fact, is very similar in the two fragments compared to the periodic system. And so it reflects the fact that the effect of the environment in the MOF on the screen is very low. And so this explains why we have such a strongly bound epsilon, because the excitations are localized into specific students, and then the screen is relatively small. So now this is a kind of ongoing work. So the idea was kind of to understand a little bit why in certain cases we have excitations that depend a lot on the starting point functional, and in other cases they don't. So you remember my first slide here on the change of the S1, when we increase the amount of exact exchange, while the pi-pi-star excitation is fairly constant, like the case of MOF, of the MOF, vectors I showed you, sorry, go back here, even for the MOF, the GW gap and the BSE gap in this case is very, very similar. And this is kind of similar to results obtained here by the Yenko workings, in which when computing the difference in the excitation energy, BSE energy, between a starting point as the MO6 and starting point MO6, they found that actually the change is larger for the n-pi-star excitation compared to the pi-pi-star with the n-pi-star. So if, because for example, in this case, so this is an n-pi-star excitation, this is a pi-pi-star excitation, because the electron is the same. So our first assumption is maybe what is changing is the hole, and this is what's giving these huge differences. So that the hole is responsible for this dependence. So we extend with our analysis to the true Largagliati set here, and I'm reporting here the change in BSE computed using a starting point of PBH 50% minus the starting point, oh sorry, and PB, sorry, if there was a mistake. Plotted against the change in the hole density, and what we see in fact is that there is no correlation at all. So we went back and said, okay, maybe then if we extend our sample of molecules, we don't find such difference between the n-pi-star excitation, pi-pi-star excitation. And this is what we did. So we used two different sets of molecules. And again, I'm plotting the change in the BSE energy. And in fact, so the black are the n-pi-star excitation, the orange are the pi-pi-star excitation, and the small orange are the excitations that we computed that were not reported in previous studies and literatures, and are the same, of course, excitations, and the excitation coming from the same molecule as the big black dot, and also are excitations that have the same hole, the same electron, the same pi-star excitation. And we can see, in fact, that there's really not a difference between pi and pi-star excitation, and that the same molecule can have a larger or small difference depending on the case. So, okay, so we couldn't answer this question, but it would be interesting to understand a priori which case we can expect larger effects so that we can act accordingly. So we adopted again this orbital-tuning scheme. Please look at the top table first. So what we see, in fact, again, we go from PDE to PDH from 0 to 1%, and then we go from the orbital-tuning. And we see, so we compare, so these are the errors computed. So we have the mean sign, the minimum signed error, with respect to coupled cluster and experiment. I think it's fair to compute with coupled cluster more than experiment, because in some cases they've been performed in solution. So in fact, what we see is that the mean sign error is negative and it decreases, which reflects the fact that there is a dependence on the underlying GW eigenvalues, which I'm showing now on the bottom of the slide. So now here I'm showing that the change in the BSE, again, between 50% and 0% among rejected streams, as a function of the change in the eigenvalue energy of the levels that are involved in the BSE excitation that can result in here. So what we see is that the correlation is there, but is weak. So there are some cases where really they are not on the XY line, and this is where the effect of the wave function enters. So the conclusion is that there is a dependence both on the starting point eigenvalue and on the wave function. We cannot really separate the two because we don't have a reference for the GW eigenvalues. But so we think that nonetheless, using this orbital-tuning scheme, since it is the smallest error, it's still a fair way to proceed when there might be a dependence on the starting point of the function. So to conclude, so I talked about this environment consistent orbital-tuning scheme that works relatively well for different kind of molecules. So if for the photoswitch matrix described this the optical excitations and show that you can use the fragment model with a very good decent qualitative review, but it cannot be quantitative. For this, we need the full periodic MOF. And that MOF 5 is not a semiconductor's claim until now, but rather a wide gap insulator with the very much localized excitons and low spin. And so in the ongoing work, we haven't found so the bad news is that we haven't found a descriptor that tells us which excitations and which molecules we should expect a large dependence on this starting point of function. So I would like to thank, first of all, Asim, I think he's on the audience, because most of this work was his PhD, and my precious collaborators, so Claudia, Xavier, Gabriele, and Jean, and the funding agencies, and you for your attention.
Okay, thanks a lot, Roberta. So the floor is open for question. If you want, you can raise a virtual hand and tell me. I have it in a couple of on 2 screens. Okay, can I start then, because I have when I still have some numbers in my head.
Yes.
By looking at the numbers about the peak position, when you do the full calculation, do the DFT, GW, and then Bethe-Salpeter. So it seems to me that when you start including the environment,
yeah,
not only the values changes, of course, of the GW result and the Bethe-Salpeter, but it seems that also the binding energy changes a lot. Am I right?
Mm-hmm. So probably here.
Yeah, for example, yeah. So there is a change in the values, but the binding energy, it seems to be more off, let's say, when you include the environment than when you don't.
More off. So why do you think
how to say? So if I look at the difference between the fundamental and the optical gap.
Yeah.
So if I look, there is a certain amount of energy, something like 4 electron volt, even 5 electron volt.
Okay. Yeah. So for example, if we look at 8, so 8 and 4.5, right? And then to be compared with how this difference compare between the PB0, for example, without embedding and with embedding, right?
Yeah.
What are you talking about?
So it seems that not only the values changes, Well, actually, I was looking at the top series of columns, but I mean, if it goes for the ligand, it also goes from the whole MOF. It seems that the binding energy changes.
But this we expect that the binding energy changes when you increase the environment.
Yeah. In fact, that was the question. If it is just the fact that you have more screening, and so.
I think yes. Yeah. We do expect that the binding energy decreases of the exciton, right? Because you have more screening of this charged particle, and yeah.
But okay, yes, and so since this is another number, let's say, to look at, not just the excitation energies. Now, however, I don't have the number in my head. Would your figures, when you were looking for correlation, and it was difficult to find, would this change if you, instead of looking at the energy, let's say, of the transition, would this change if you look at the binding energy, or would it be more or less the same thing?
So what is the question? The correlation between the binding...
Because here you don't find the correlation, right? It's really...
So here we don't find the correlation in terms of... So here, well, here's not really correlation plot, but here what you're trying to see is whether for certain kinds of excitation, you have a larger change than for others, right?
Yeah.
So, yeah. So here, so we don't see that there is any reason to believe that one type of excitation depends as the largest dependence on the starting point than others.
Yeah. But
this is the correlation plot.
Yeah. But no, my question was very naive in the sense that here we are always looking at the energy, the final result, let's say, of the BSE transition energies, right?
Yeah.
And another number will be the binding energy.
Yeah.
Which is so I don't know, for example, if a correlation would be less or more evident by looking at this other number rather than just the position. Just
I don't know. We can try.
Yeah.
So I think we can try, but I think what we also miss here is so here, we just have the BSE, okay? So in fact, you see that it's kind of putting together pieces trying to understand, because so from the correlation plot, you see, okay, there is a dependence. So there is a correlation of the width with the eigenvalue, with the GW. And what is missing is the effect of the wave function. And this is also reflecting from the fact that the mean signed error is negative for PD, you see here, and then it becomes more and more positive, right? Consistent with the fact that in PD, you have a very small gap and that you open it. Progressively as increase the amount of exact exchange. So these two things go hand in hand. But what the problem is to have the same kind of analysis in which you can show if this mean sign error, how much it changes when comparing the GW and not the BSE, and see if the changes in the GW are similar to the changes of the BSE. So that you can see, okay, you can see even more.
Yeah. In fact, in the meanwhile, there was a comment from Xavier saying exactly more or less the same thing. Okay, but I don't want to monopolize the entire discussion. So let's see for other question or comments about that.
I don't see the chat, by the way.
You don't see the chat?
Yeah. Now I see. Yeah, I see the chat.
Okay, other questions? Because otherwise, I have a very boring one about some more technical details. Since you can do this also in particular situation, a comparison with Fiesta, for instance, with with another code, and at a certain moment, I think I saw in the slide something about that you use the plasmon pole model for the GW. Is this an issue, or it's something that we can check if it's good enough for these molecules?
So we use the plasmon pole in Yambo, and so we haven't checked, so we don't have the proof that it's a fair thing to do. But we have, let's say that we have very decent agreement between the Fiesta and GW,
Yambo.
Fiesta and Yambo, GW value. So we think it is the case. We also think that probably plasmon excitations are very high. So I mean, it's not confirmed, but it seems that it's under control, this kind of thing.
Okay, and in Fiesta, it's not in plasmon pole, I guess.
In Fiesta, we haven't used the plasmon pole. I don't think that it is implemented the plasmon pole in Fiesta. Xavier can answer. Maybe.
Contour deformation, says Xavier. Okay.
Yeah, this is what we use. Yeah, contour deformation. But I don't think there is the option to do plasmon pole.
No, but it's good to know that you obtain the same results. Okay. Okay. I don't see.
So regarding what it's now the chart. So what Xavier says, excitonic binding energy is much less sensitive to environment. Yes, this is true, but I think the question was regarding the correlation, right? I know you did have a question.
Yeah, but it was sort of related because indeed the binding energy is even less sensitive in this respect. Maybe okay, Mebarek, please.
Okay, can you hear me?
Definitely.
Can you actually simulate the pressure on the molecule by the environment, for instance?
Like hydrostatic pressure?
Yes, hydrostatic pressure, because the environment, I mean, you can embed, for example, a molecule in some environment, like here in IPCMS, I mean, they can do this kind of experiment. Is it possible to simulate this by changing and see the tendency, what happened to the excitonic gap and so on?
I guess you can try, you can change your environment and see what is the response. But it's a model that takes into account, it's the electric model. So in order to account for the hydrostatic pressure, I don't know, maybe you can use the pressure yourself, like DFT and see the effect. I don't know if in the PCM or SMD model, you can do this kind of things with the pressure. But you can separate the two. So you can have the response of the material in terms of the electric and the response and the effect of the pressure that you can keep like.
Yeah, but even for a dielectric, I mean, it's sensitive to the pressure, actually. Right?
Yeah, I don't think you can correlate this response to some kind of pressure. I don't know.
It's indirect, but
yeah, maybe yes.
Thank you.
Yeah, sure.
Okay. Okay, I don't see other question or comments. At the end, it was exactly on time. And okay then. And well, for Roberta, since you're here, for what concern the school, everything is confirmed, right? So
everything
I guess
is confirmed. I will send an email beginning next week with the details. So like arrival, tram, stops, etc. I will also send an email as soon as I get the confirmation from the restaurants to ask you for the menu, because we need to have the different choices. And then we are all set up.
Perfect. We all can wait for this another exciting event. Okay.
Cool.
Well then, in this case, I will say thank you again, and Happy New Year again for everybody. And well, let's keep in touch for the next webinars and other events. Okay. Okay. Bye bye, everybody.